Let's go ahead and introduce an example that contains a lot of the elements of what we've just been talking about. So we have a solid, and I'm going to look at the side view. So it is a rectangular parallelepiped, and it is going to be fixed at the base, and it is 200 millimeters in width. And the side view, then from the other angle, it's going to look like this. And that dimension is 100 millimeters. So that one, I'll put some little arrows on it. So 100 millimeters. It obviously also has a length this way, but that's not going to be relevant for our analysis. So we won't need that one. So it's basically 200 millimeters wide, 100 millimeters thick. And we're going to put an axial compressive load on this one. Now, what is sometimes done is to put a rigid block on top of this elastic solid. And I'm going to put it like so. The reason that that's done is a lot of times you'll see the load like this. So there's P, there's another view of P. And the reason that that's done is to evenly distribute the load from a point load that's acting right at this location to something that's more uniform. So this block, we'll put it like there, rigid. It's really more a matter of style. So off to the side, its purpose is to go from a point load at one location to basically evening things out. So it's a point load to, let's call it uniform stress. So what that means is rather than having a applied load being thought of, if we take a pencil lead and stick it into our hand, it's going to really hurt at the location where we apply the load. And instead, what we're really doing is we're saying, okay, you're immediately going to go from a point load like this to something that looks more like this. So that's going to be the equal and opposite compressive stress that we will have. So basically, the rigid block here acts to evenly distribute the load so we can more easily envision a state of uniform stress. Now, in this particular problem, we're given the following. We are given an angle, so if this is from the horizontal cut, then we're given a cut, and I'm going to try to draw it this way, like so. This may not be to scale. And the angle is this one, and that's going to be 36 degrees. So that is the geometry that we have for our particular section. And in this case, we're actually given the normal stress on that particular plane. So sigma on that plane then is going to be equal to 12 MPa, and that's going to be compression or negative. So it's pushing back up against. Now we can immediately then draw that particular field of arrows like so. We would draw it like this, and it goes into the board also. So now it's acting perpendicular to the cut surface, and its value would be 12 MPa. Now remember, M means mega, which is 10 to the 6th. And again, pascals is newtons per square meter. Just to remind you, those should be really embedded in your soul at this point, but just in case you've forgotten it, remember you got to pick those things up. So that calls out then that we're going to be using SI units. Okay, so we've got that particular value of stress that's acting on that cut face. And now the questions become, first off, what is P? In other words, what's the load that is causing that? Second, what is the value of the shear stress on that cut plane? And then finally, find the values of sigma max and tau max. So those are the three questions that were being asked during this particular example. Now, here is the big watch out. Let me shrink this down a little bit, and I will say, watch it. This is exactly what I warned about at the tail end of the last lecture, because in this case, the angle is not given from the perpendicular cut. This 36 is actually the complementary angle to that. So the theta in our expressions And incidentally, that expression is not just being used by us in this class, it's being used by countless other textbook authors. So it's very common to write that angle as a function of the perpendicular cut. So theta in our expressions is not 36 degrees. Exclamation point. We're very excited about that. Instead, it's this one right inside here. It's the angle off of the perpendicular cut. So theta is going to actually be 90 minus 36 degrees. So that's going to be 54. 54 degrees. That's very important. It's kind of a subtle point, but as long as you realize it, then it makes things very, very easy for us. And now it becomes just a matter of simple substitution, because we can use then the fact that sigma is equal to P over 2a, and it's okay if you have to look this up, 1 plus the cosine of 2 theta. And now that angle, let's go ahead and substitute these things in. We know then that the theta is going to be 54 degrees. And we make sure to hit degrees on our calculator button. Don't put it in radians. So degrees on our calculator button. Be careful about that. And the other expression, P, is of course unknown. We don't know what that is. Sigma is given. We're given the area. We're given the angle theta. So P is the only unknown. Now we have to be careful about the area, though. Remember, we're dealing with SI units, and as soon as we say, let's draw this off to the side, as soon as we say Pascal, it is newtons per squared meter. So that means that we're going to have to convert the distances into meters. So remember, that's 3 decimal point moves. So we're going to have P divided by twice, and the area is the 200 millimeters, so it's 123, so that's going to be 0.2 times 100 millimeters. We put the decimal point after the 100, move it 3 to the left, and that's going to be 0.1. So that's going to be our area that we have, those two multiplied by each other. And then we have, that's all multiplied by 1 plus the cosine then of 108 degrees. And then the sigma is 12 times 10 to the 6th. That's the 12 MPa. So we have one equation, one unknown, and we find then that P is equal to 694.700 newtons. And so frequently we will go ahead and use a prefix on the newtons. So we can go 1, 2, 3. That's going to be 694.7 kilonewtons. So P is 694.7 kN. So that would be our boxed answer. And again, on your homework and so on, if we did have a grader, then that would be one that you would want to highlight. But always kind of draw attention to your final answer. So that's just a matter of style and good manners. So a box around the answer is a good practice to develop. And now that we've got P, of course, it's off to the races. Once we have P, so now that we have P, it is very easy. The next expression then is going to be the shear stress. So that's tau is P divided by 2a times the sine of 2 theta. And again, it's okay if you have to look that up. Don't feel any embarrassment about that. But that's going to be 694.7 times 10 to the 3rd. Remember to convert that now back into newtons. And then that's going to be divided by twice, 0.2, 0.1, times the sine then of double the angle. That's going to be 108 degrees. So when we do that, we find that tau is equal to 16.51 times 10 to the 6th pascals. And then the 10 to the 6th is mega, so we say tau is equal to 16.51 MPa. So there's our answer for that. Incidentally, remember that the P, it is shown as going down like this. Now remember, you assumed in your statics class that if a force was a tensile, it was typically positive on a section like this. If it's compressive, it's negative. But in this case, we really don't worry about giving a sign to P because its physical direction is shown. So you don't really need a sign on the value of the axial force when you've got a picture to go along with it. We're not going to be that nitpicky about things. Now, you should understand that it is a compressive load, and that's a good thing to kind of have in your mind, but you don't really need to indicate that in your answer because it is going down like that. All right, so now that we have the value of the shear stress on the plane, we can also get the max values. So the max values we just have as, and we can use our knowledge that, remember, the max value is P over A for the normal stress. That occurs when theta is 0. So it doesn't mean find the maximum stress on that cut plane. It means find the maximum stress anywhere. So this is going to occur if this is our segment. What would happen if we made the cut like that? So that's what they mean by finding the maximum normal stress. Find it on any cut plane, not the one that we've just done. So that's just going to be P divided by A. So that is going to be our 694.7 times 10 to the third. And then we have the total cut area. So that's 0.2 by 0.1. So those are our values that we get. And so the maximum value, I should write max over here. So sigma max, in this particular case, is just equal to 34.7 MPa. And we would want to go ahead and write compression right there, just to make sure that people know that this thing is being pushed on rather than it's being pulled. Now the cool thing about this, remember that tau max is just half of sigma max. Sigma max divided by 2. Remember, it was P over A versus the P over 2A. So it's just going to be 1/2. So that's going to be equal to 17.35 MPa. And now there is no sign. You don't have to put, there is no such thing as T or C for the shear. Remember that we're kind of tabling the concept of the sign of the shear stress for right now. So you don't have to worry about that. You don't have to say anything about shear. You just have the magnitude only. All right, that is our first example for the case of the stress on an inclined plane, and really one is all that we really need to do. So we'll have you rep that a few times just to make sure you've got it. And we're ending our part B.